This is the homework for the 231 portion of Chemistry 410. The first question asks us about orbitals and where the lone pair here resides. And so we're going to look at this nitrogen, and it has a double bond to the left, an NH bond to the lower right, and the lone pair. So there are three electron groups here, or three regions of electrons, and so that leads us to sp2, and that's sp2 plus p. Of course, the p orbital is used to make the double bond, so B is the best choice here. How many sp3 carbons are in this molecule? Well, sp3 carbons are those that have 4 electron groups around them, 4 single bonds typically, and that's going to be the 2 CF3 groups. So there's really only 2 sp3 carbons. There are 2 sp2 carbons. Those are part of the carbonyl. Which of the compounds listed below would be expected to have the highest boiling point? And so that's going to be the ones with probably the strongest intermolecular forces. We observe that compound 2 has an OH group, and that leads to H bonding, or hydrogen bonding. That is the strongest intermolecular force. There's nothing here. There's nothing for number 1. There's only London forces. For number 3, there is a chlorine that could lead to dipole forces. And for number 4, there is an ether, which could lead to slight dipole forces, but nothing has anything close to hydrogen bonding. So we would choose molecule 2. It has hydrogen bonding. Which functional groups are present in this molecule? So there's a couple that we can observe. There's the CO double bond, there's the CC double bond, and that's really it. So we're looking for ketone and alkene, and that would be C is the right answer here, ketone and alkene. Is the compound in the box acting as an acid or a base? So in the box here, we see this ketone, acetone, and in this case, we are removing a hydrogen using the O-. That hydrogen is coming from this CH3 to result in these two resulting products. And so we see that the acetone is acting as the acid. It is giving up a hydrogen to the carboxylate. This is the T-butoxide is the base. Acetone is the acid in this case. Predict the position of equilibrium for this reaction. Here we need to remember acid-base, perhaps ARIO out of the Klein textbook would be a good strategy here. We think about the atoms, and there is a C- versus a C-. There's no difference in atoms. And so really our goal here is to decide which of these bases that I've highlighted with the arrow is more stable. And that's the side that will be favored at equilibrium, the more stable base, less reactive. So atoms are the same, carbon, resonance. There is no resonance for either of these anions. Induction, there is no extra electronegative groups nearby the anions that might help to stabilize it. And that leaves us only with O for orbital. And so these are in different orbitals. This is an sp3 orbital. This is an sp2 orbital. And so the difference in orbitals tells us that this is the more stable anion because there is more S character for the sp2 hybridized orbital, and that helps to stabilize the negative charge. So the sp2. So the position of equilibrium then would lie to the more stable anion, and that would be to the right. Which of these drawings is a constitutional isomer of I? So I here is a cyclohexane ring. if you want to count carbons and hydrogens, you'll come up with C6H12. And we know that a constitutional isomer needs to have the same formula, but a different connectivity. Hexane itself does not have the same formula. It has C6H14. You can count those hydrogens on your own. This has C5. That doesn't count. And this molecule over here is an isomer of hexane. It also has C6H14. And that leaves us with this molecule in the upper right. And if you count carbons, you come up with C6. If you count hydrogens, you'll find that there are not 14, there are 12. And so that molecule is the constitutional isomer of 1. Here we're asked about Newman projections. This Newman projection here corresponds to which molecule? So when I look at this, I'm going to essentially translate the Newman projection into a drawing. First, I want to figure out how many carbons there are and if there are any branch points. So there's a carbon here, 2 carbons. Remember that the the intersection here is a 3rd carbon, and this circle represents the back carbon of our carbon-carbon bond. That is the Newman projection representation. So that's carbon 4, and then we have carbon 5 and 6, and there are 6. So all 6 of these carbons are in a row. There are no branches, and so if I were to draw just the carbon structure, I would get this. And I can put a bunch of H's on there. I'm not going to draw that here. And that's it. This is the carbon structure. It is full of hydrogens, of course, and we can draw those in. But what is the name of this molecule? Well, this is, of course, hexane. No branches, 6 carbons in a row. We have hexane. What is the major product of this reaction? So here we have some Br2. We have methyl cyclohexane. And this is sunlight. H nu stands for light energy, and this is a very special case. This is a radical reaction. You might want to review part of Chapter 11. There might be a radical of some sort that appears on some of these standardized tests. Most of our Chem 231 classes didn't have a chance to get to Chapter 11, and even if there is a radical question on a standardized test, there's probably only one. There's not going to be a whole host of these questions. So if you have a chance to review, that's Chapter 11 in your Klein textbook. But essentially, what happens in a radical reaction is that we're going to put a bromine on the sort of the most substituted carbon. So the bromine will be added to this carbon right here. And so A would be the best choice here. The most stable conformation of cis-1,3-dimethyl cyclohexane has how many hydrogen atoms in axial positions? So this is a cyclohexane. We're talking about axial positions. And so it probably would be a good idea to draw this. And so let's draw a chair structure. And so it's cis-1,3. That means the methyls are on the same side. And we know that the most stable, to get the most stable, we want equatorial positions for as many of our substituents as possible. So I'm going to start with an equatorial position here. Try that again. Sometimes it takes. So there's my equatorial position. And then if I go over to the 3rd carbon, here's where I'm going to start my other one. Cis means it's in the same direction. So this is equatorial and up. I want another equatorial and up. So there's my cis-1,3-dimethylcyclohexane. So how many hydrogens here are in axial positions? Well, I haven't taken up any axial positions with my 2 methyls. And that leaves 6 axials. And let's put those in red. I'm not going to put the H's on there. And of course, every cyclohexane has 6 axial positions. They're not always containing hydrogen, although in this case they are. So we would answer 6 because our 2 methyls are both in equatorial positions. What's the proper name for this molecule? Let's see, so we have cyclohexane, so we want to make sure that all 5 choices have a cyclohexane here, and it looks like they do. And then we have, let's see, we have a methyl on 1 carbon, and 4 carbons away we have this T-butyl group. And you can redraw this if you wish. This is simply 3 methyls coming off of that 1 carbon. So that's a T-butyl group. And we'll notice that both are up. So that means we have a cis. And so that means we can cross off some of these that don't say cis. So C says axial equatorial. We never use those terms when we're naming something. We can cross off B, and we can cross off E. And that leaves us with A and D. And we can cross off D, I think, because this is cis-1 isopropyl. We don't have an isopropyl group. We have T-butyl. So cis-1 T-butyl, 4-methyl cyclohexane is the best choice for the name of this compound. Number 12, how would you describe the relationship between the following 2 molecules? These are Fischer projections. And you can look at these probably at the end of chapter 5. I'm not going to go through how to analyze them right now, but what's important to look at is that they appear to almost be mirror images of each other if we put a mirror right there. However, the fluorine and the hydrogen are the same down in that bottom carbon, where everything else is, I'm sorry, they're flipped, they're the same, where everything else is a mirror image, and so that would give us diastereomers. Remember that diastereomers require some of our stereocenters to be flipped, and there are several stereocenters here. Let's try to identify them. This is a stereocenter, this is a stereocenter, this is a stereocenter. Same thing with this molecule. There are 3 stereocenters there. So there are 3 stereocenters. 2 of them get flipped as we go from molecule 1 to molecule 3. 1 of them remains the same. And so that fits the definition of diastereomer. What is the absolute stereochemistry of the chiral carbon here? So the chiral carbon is this carbon, and the bromine gets priority 1, the rest, the longest part of the chain gets 2, methyl gets 3, and I'll put the H right here, that gets 4. And so if we count 1, 2, 3, we're going counterclockwise. The H is in the correct position, which is back, so this is S. If the reaction rate of the following reaction is X, then doubling the concentration of KCN would give what rate? And so first we sort of have to decide what kind of mechanism we're looking at here. We're in acetone, we have a good nucleophile, we don't have a good base. So this is probably an SN2 reaction. And thus, if we double the concentration of the nucleophile, we should double the rate. We know that the nucleophile plays a role in the mechanism, so does the substrate play a role, so doubling either one of them should double the rate. So we would expect the rate to be twice as fast if we double the amount of KCN that's present. Number 15, what is the major product of this reaction? So we have NaSH, again a good nucleophile. We've got acetone, which is a good indication that this is probably SN2, and again we have a nice chiral alkyl halide here. And so we're going to look for inversion of stereochemistry. If it were SN1, we'd look for a racemic mixture, or more or less a racemic mixture. And so that gives us C. C is the best choice here. It shows inversion. We wouldn't choose B because that gives us a racemic mixture, and we would not choose A because that does not show inversion. That shows the same relative stereochemistry. Number 16, which of these is the best electrophile? And so electrophile is a good acceptor of electrons, right? It's going to be possibly positive charged or have a large delta plus. A here has the only positive charge. It's a cation, and cations are great electrophile. So A should be the best choice for this question. Number 17. The major product of this reaction will result from what type of reaction? So here we're asked to figure out what the mechanism is. So we again have a good nucleophile. We've got a tertiary site here. That's a pretty good indication as to what to expect. We probably will not have not E1 or E2 because we have a good nucleophile. So let's cross those off. And then tertiary favors SN1 very much over SN2. So we know that it's not SN2 because the fact that it's tertiary. So we're going to choose B. We're going to choose B as our favorite answer here. All right, which of these choices is true of these reactions? So we have a trans cyclohexane ring with a bromine and a T-butyl, and we have a cis cyclohexane ring with a bromine and a T-butyl, and we're going to do E2 reactions here. In this case, it's important to remember that we need certain stereochemistry to react in this E2. So let's draw the cis. Let's draw the chair structure of the cis. And we know that the T-butyl is up, and we also know that T-butyl will almost 100% favor being in the equatorial position. So we're going to put it there right away. That's up and equatorial where I drew it. And then on the carbon on the opposite side of the ring, which would be this carbon, I need an up bromine. So let's put that bromine in there. And in order to affect an E2 reaction, I need to have a hydrogen 180 degrees from my leaving group. And in this case, I have a perfect setup. So this is good. This is a good setup for this E2 reaction. Let's look at the other stereoisomer. I'm going to draw the same chair. I'm going to put the T-butyl group again in the up equatorial position, except now I have a down bromine that I want to draw, and so that goes right there. And of course, this is locked in this conformation because the T-butyl group prevents the chair flip. And now the bromine cannot react. The bromine can't react. It is not in this 180-degree relationship to any hydrogen. So what that means, if we go back to the picture, this one really won't react at all. It would be very, very, very slow. The cis is a good setup for a reaction, and so that means we should choose A here. Cis would definitely react faster. Trans would not react faster. They would not react at the same rates. No reaction is expected. That's untrue because we've decided that the cis positions the bromine for a good reaction. And the product shown would not be formed. That's not true either because, again, we have our chair structure here that shows the H and the bromine in perfect position to make the expected or the product indicated on the paper. Number 19, determine the product of this reaction. Here we have a alkyne, and if I can draw carefully, there's a little H at the end there. That H is reasonably acidic, especially when we use sodium amide, the strong base. And so once we remove that hydrogen, we end up with this situation, and that's a decent nucleophile. And that nucleophile can participate in an SN2 reaction that looks like this. So we're going to make a new carbon-carbon bond. We're actually going to add that cyclohexane ring plus a carbon to the end of our alkyne. And so you should be able to come up with B as the expected product from the arrow push that I drew right there. So B would be the correct product here. What is the product of the following reaction? So here we have an alkene, and we're going to add Br2 to this alkene. That's going to add in a anti fashion. So we want to make sure that our stereochemistry here is anti. So we could think about it like this. And I'm going to abbreviate with phenyl. Maybe I have one bromine up and the other one down, and that would be the product. Now, which of these choices matches what I just drew? It's not the first one, because that only has one bromine. It's not the third one, because that has two bromines, but they're both in wedges. Plus, it indicates that we made a racemic mixture, which could be true. And we're not going to make the alkyne either. We're going to make this 1,2 dihalide. That's going to be this structure. More appropriately, we probably should have plus minus here, because we do make a mixture of enantiomers depending on where the second bromine comes in. So more appropriately, that should have the plus minus. Okay, so number 21. Of these shown, which would produce the product below upon treatment with ozone, followed by zinc, metal, and water? So this is the ozonolysis reaction, and we talked about this in class, O3 and then zinc and water. We might have used DMS in class, but they both do the same thing. And so what you could do is connect these two oxygens, remove the oxygens, connect the double bonds together, and figure out how it would look. And so how do I do that? Well, I'm just going to number from those carbonyl carbons. So 1, 2, 3, 4, 5, 6. So I'm looking for a 6-membered ring, which I have. I'm looking for a 6-membered ring with a methyl group on carbon 1, on carbon 2, and on carbon 5. So let's look at that. Let's look at that crosses off 2. That only has 2 methyl groups. 3 has 4 methyl groups. So does 4, and so does 5. So that really did our answer for us. Let's just double check though. If we're going to just randomly number like this, we can actually get our numbering scheme to line up with the numbering scheme I used on the original molecule. This is not the numbering scheme we'd use to name the molecule. It's just a random numbering scheme I used to track the methyls. But we see, though, that there's a methyl on 1, 2, and 5, and that's exactly what we were looking for. So 1 here is the best choice for this molecule. What is the nucleophile in this reaction? Well, we have a tertiary substrate, we have water, and we've produced the alcohol through some sort of substitution reaction, and that means water is our nucleophile. That should be pretty obvious. This is your standard SN1 type reaction. 23, what would be the primary mechanism for this reaction? Here we have strong base. Actually, if you look at Klein, it's strong base and strong nuke. And here we have primary alkyl halide. I would say that we're going to favor SN2 over E2. The primary mechanism would proceed by SN2 because of our primary halide. If it were secondary or tertiary, we definitely favor E2. But this is primary, so we're going to favor SN2. Which of these structures depicts the most stable carbocation intermediate? Now remember that primary are not as stable as secondary, are not as stable as tertiary. So really we're going to look for a tertiary cation, and that's right here. So number 2 is most stable. It has the tertiary cation. The rest of these are primary, secondary, secondary, secondary. Well, number 2 is tertiary. So we're looking for the most stable cation. It's tertiary. Lastly, give the IUPAC name for this compound. We want to try to come up with a name, I think, is the easiest way to do this. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 carbons. It should be octene. I started numbering nearest the alkene. So this is 3-octene. I did not number from the left side. That would be far from the alkene. And so that can cross off some of these for us. C and D are not 3-octenes. A, B, and E are. And then we have a 2-methyl, a 5-methyl. So 2,5-dimethyl. Which of these has 2,5-dimethyl? Well, E does not, so we can get rid of that one. So these are both 4-ethyl, 2,5-dimethyl, 3-octene. We need to figure out if this is E or Z. Remember that E and Z refer to the highest priority group on each side of the alkene and how it's related to our imaginary railroad track line. So on carbon 3, there are 2 groups, the isopropyl and the H that's not drawn. The isopropyl is the higher priority group. On carbon 4, the other carbon of the alkene, there are 2 groups. There's the ethyl group pointed up, and the rest of the molecule pointed to the left. And that rest of the molecule is, of course, the higher priority group. It's bigger, and it has a branch nearer to the alkene. And so my 2 blue dots, then, are on either side of the alkene. That leads to the E stereochemistry. So that allows us to choose A as the name of this compound, according to the IUPAC rules.